Okay, good evening. Okay, good evening, everyone. My name is Alan. I'm a Solidity developer, and I'm also a member of DappLearning community. It is my great honor to be here to talk about smart contract development using Foundry. First, allow me to introduce DappLearning community. DappLearning community is a non-profit organization that designed for developers to step into blockchain app development. Where developers can learn DeFi, NFT, DAO, crypto, etc. knowledges. And we hope we could not only give junior developers a feasible and easy to learn learning roadmap. We hope we also can present advanced developers a platform to communicate and to cooperate. Here in DappLearning community, we have three major components. First is our GitHub repo. You can see here github.dapplearning.com/dapplearning. And in our GitHub repo, we provide a list of learning tasks in our repo, and developers can work their way through these tasks from easy to difficult to learn the app development. And we also organize a weekly meeting where developers can share their technical presentation in our weekly meeting. We have invited a lot of people from well-known projects to give technical presentations. And we also have a translation team that have translated the MIT open course Blockchain and Money, which we think is a very great material for beginner to learn about blockchain and improve their financial knowledge. Okay, so much for the introduction. Let's move on to today's workshop. In today's workshop, I will do a live coding and demonstrate how to use the Foundry framework to develop, test, and deploy a WETH token contract. And I hope by the end of this workshop, we'll be more familiar with the workflow of smart contract development. So, what is a WETH contract? WETH stands for wrapped Ether. Ether as the native coin in Ethereum blockchain is not ERC20 compatible. So if we want to take part in some DeFi project, we need to first wrap our Ether coin into a wrapped Ether token and at a 1-to-1 ratio. So today we are going to build this wrapped Ether contract. And our wrapped Ether contract should be ERC20 compatible. And the people can deposit their Ether and receive wrapped Ether at a 1-to-1 ratio. People should also be able to unwrap or withdraw their Ether at a 1-to-1 ratio. Today we'll be using a framework called Foundry to develop our smart contract. Foundry is a portable, fast, and modular toolkit for Ethereum application development. And it is written in Rust, so it's blazingly fast. It consists of 3 components. The major one is called Forge. Forge is an EVM smart contract developing and testing framework. The function is like truffle and hard hat, but in truffle and hard hat, we need to write our tests in JavaScript or TypeScript. So it requires us to learn a lot of API and libraries. It also requires us to change from Solidity to JavaScript and back to Solidity during our development. It's a lot of context switch, and context switching costs our focus. On the contrary, in Foundry, we write our smart contract in Solidity, we write our tests in Solidity, and we can also write scripts in Solidity. So no context switching, and we will have a better developer experience during development. Other than Forge, Foundry provides a CLI to Codecast. It's a toolkit for interacting with smart contract, for sending transaction, for reading data from blockchain. And Foundry also has a tool called Anvil. By using Anvil, we can spin up a local Ethereum node. It's just like Ganesh and the hard hat node, but much faster. Okay, here goes to our live coding. First, we need to install Foundry. To install Foundry, we can go to a website called getfoundry.sh. It will show us a command. If you are in Linux or Mac, you can run this command and it will install a tool called Foundry app. And then you can just run Foundry app to update your Foundry to the latest version. Yeah, you can use Foundry app to install Foundry, and you can use Foundry app to update your Foundry. However, if you are on Windows, you need to build from source. You need to install Rust and git clone the Foundry repo and then build it from the source. You can look the instruction in getfoundry.sh website. Okay. After installing Foundry, we can use Forge. You need a project, and we can choose the project name. Here we use WETH as my project name. I already have this, so I delete it first, and then you need WETH here. Okay, then you need a project called WETH. And let's go inside and see the project layout. All our source files the source directory includes all the source file for our smart contract, and the test directory includes all the test case for our smart contract. And all the test file by convention, it ends with .t.sol. And likewise, the script folder includes all our script. It ends with .s.sol. All our dependencies or our libraries are in the lib folder. You can see here, we already have a Forge standard library. And in this example project, we also have a foundry.toml file. all the configuration parameters we can write it in this foundry.toml file. Okay, that's how to init a project. We are going to write the wrapped ether contract, and wrapped ether itself is a ERC20 contract. So we can use the ERC20 implementation from the OpenZeppelin library. Then how can we import external library into our project? We can do it by using forge install and followed by the GitHub repo OpenZeppelin/OpenZeppelin contracts. We can also add a tag or the commit, append the commit after this if we want. Okay, after installing the dependency, let's check the app folder. We can see we have downloaded this OpenZeppelin contracts. We can use forge remappings to check all the remappings Foundry made. Foundry framework automatically calculate the remapping for our dependency. If we by using this remapping, instead of import a contract using this path, we can use the path in the from. If we want to change this path or change the name of it, we can write in a file called mappings.txt, or we can first type the default remappings to this remapping.txt file, and we edit it. Here we added the name for the OpenZeppelin contract so that it is compatible with the import path in Hardhat. Okay, after this here we already have an example source file called counter. We copy it and rename it to weth.so. And first we delete all the content and rename it to weth. weth is the contract we want. And here we can use forge build. Here we can use forge build to build our project. After forge build, we can see there are two extra folders. One is cache, saving all the cache file. One is out, saving all the output file after compilation. We can see what's inside our out file. It has a JSON file, and inside this JSON file, we can see all the API or the bytecodes, etc. Okay, like we said, we want to import the ERC20 contract from OpenZeppelin. We can do it by import. And we inherit from this. Here we can specify our contract name to be my wrapped ether. And the symbol for our ES20 token to be MYWETH. Okay. And we can first build it to see if there is any compilation error. Or we can use forge build dot forge build forge build Dapp to run it in a watch mode. So what is a watch mode? In a watch mode, there is a watcher watch for your file change. So every time we change our source file and save it, the watcher will run forge build again. So if there's any syntax error, we can recognize it immediately. Okay, so my habit for smart contract development is to write a stack, write all the external functions and write a stack skeleton for this contract. Then use a test-driven approach to write test first, and then go back to the contract to write the implementations. So here I will demonstrate my test-driven approach. For our wrapped user token, we need first the deposit function so that people can deposit their ether and get wrapped user in return. And I will skip the implementation for now. We will also have a withdraw function to go it the opposite way. People can use the withdraw function to decrease their wrapped user balance and get their ether back. Okay, the compilation passed. Now let's open a new terminal and introduce Foundry test. So Foundry test 101. How to do testing in Foundry framework. First, we rename the test file to weth.so. And we delete all the contents from this contract. Here we will use a simple function, external function or public function that starts with test. And let's run forge test and see what's happening. It shows us the test result, pass, test. So Foundry test 101, what is a test case in Foundry? In Foundry, all the external or public function that starts with test will be treated as a test case. And if the test case reward the test failed. Otherwise, it passed. Here we can see the test 2 failed, and the test 1 passed. Okay, so what is this import? Why is this the import forge standard test also in the example file? Here we import a test contract from the forge standard library. By inheriting from this test contract, we gain 3 major capabilities. The first one is the capability to do assertion. For example, here I make 2 variables A and B. I can do assertion using assert equal A, B to assert that these 2 variable equals. And here we need to increase the verbosity level to level 2. After using 2v in our argument, we can see the log result. And here we can see the log result from our assertion. And we can also use assert grade to do assertion. And we can use assert less than to do assertion. This assertion should pass right, like we expected. So the first functionality in this test contract is to give us the ability to do assertion. And the second functionality is to help us to log more information out. Let me show you how. In this test contract, it defines many log events. Starts with log, and we can emit this event by using emit event name and the parameter. By doing so, we can emit our result in the test result. Okay, the test contract provides us the ability to do assertion, to log more information. What's more important about this test contract is that it provides us the ability to use cheat code to change the state of the VM, the Ethereum virtual machine. By using this cheat code, you can see you are in a super mode. Let me demonstrate how. The most used one of the most used cheat code is VM the DappLearning. It allows you to mock a user. For example, here I have an external function. Oh, I forgot to mention this console2 library. In forge test, you can log information by using log events to emit. You can also use console or console2 library that provided by this test contract and use console2.log to log information. Okay, it logs this information. And here I want to log the message sender for this function. I want to know who makes the message call to this function. And I can add extra information as parameter. So if we call this function this way by using this dot function name, the caller would be this contract address. I didn't save it in this file. Okay. So this contract address is B for C, and the caller for this inner function is the same. If we use the cheat code VM.rank, we can pretend to be anyone. We can pretend to be any address, even if we don't have the private key for that address. So by adding VM.rank, let's see. Okay, the caller for the inner function is address 1. And yeah, by using this cheat code, we can mock a user and send a message call from that user. Even if we don't have the private key, we don't have the ownership of that address. The other cheat code most used is called VM.deal. It can set the balance of an address to some value. For example, we can use this make address function from this test contract to set an address called Alice, and let's see the initial balance of Alice. Ooh, it's 0. And let's try to change it. We can use VM.deal to set the balance of ether for Alice to 1 ether, or maybe we can try 100 ether, and let's see. Okay, now Alice has 100 ether in this test environment. Okay, after introducing the usage of forge tests, let's go back to our wrapped ether contract and write the unit test for this contract. First, we want to write a unit test for deposit. Here we import the wrapped user contract, and in this test case, we first deploy a wrapped user contract by using this new syntax, and then we mock a user named Alice. We can also give Alice some initial balance, like 2 Ether. Is the range, and then goes the act. The act is we make the deposit call from Alice, and the value for the message call, we can set it to 1 Ether. So it means Alice send 1 Ether to this wrapped Ether contract by sending a message call to a deposit function. And after this act, we should make some assertion. Here, the result, here the assertion we can make is that after deposit, the balance of Alice should be 1 Ether. And 1 Ether is an amount, not the value. Okay, so here is our unit test for deposit function. We can try to run it first. Okay, it failed as expected. And we move back to our source file, our wrapped user contract, and finish the implementation for deposit. The solution for this is quite easy actually. We can use the underscore mint function from the ERC20 implementation in OpenDapp-Learning library. Here we only need to mint the message value amount of wrapped Ether token to the message sender. Okay, let's go back to our test and see if this test passed. Okay, this test passed. Test deposit passed as we expected. Then we move on to write the unit test for our withdraw function. We will also follow the arrange, the act, the assert step. And here we deploy our wrapped user contract first. We mock a user called Alice, and we give Alice 2 Ether balance. And here we first ask Alice to deposit 1 Ether into our wrapped user contract. Then we ask Alice to withdraw 1 Ether from our contract. After deposit and withdraw, the assertion we can make is that the wrapped ether balance for Alice should be 0 by now. Okay, we can use for build to see if there's any syntax error. The test builds successfully. Then we go back to our source contract and how to implement this withdraw logic. It's also quite simple. First, we burn some amount from the message sender. Which means we decrease the balance for message sender by this amount. And then we send the amount of ether back to this user. Okay, so this is withdraw. And we save this file. We go back to our test. We run our test. Okay, our test passed. If we increase our verbosity to -4V, we can not only see all the logs info, not only the log info, we can also see the call traces for each test case. What is a call trace? Inside these call traces, we can see all the gas usage for function call. We can see the contract and the function name. We can also see the parameter and the return value, and also all the events emitted during this test case. So checking the call traces is very helpful during debugging. And if we use verbosity level 3 -v, we only show the call traces for failing case. So if I change this to 0.5 to intentionally make this test case fail, we are expected to see this, to see the call traces for this case, right? Okay, here we have the unit test for our wrapped ether contract. We can do some refactoring. Each test case in Foundry is independent. You can see it as a simulation. So what's happening inside one test case will not affect the other test case. But sometimes we have some logic that is shared between each test case. We can extract this logic into a function called setup. Like this one, like this topic, like this logic. So by adding a function called setup, each test case will first run the logic inside setup and then run the logic inside each test case. Here we can extract these two variables into storage to make it global. So after this refactoring, Republic. Yeah, after this refactoring, the two unit tests passed as expected. Okay, that's so much for test. Let's move on to scripting. Let's rename this file to eth.s. So okay, a barebone function, a barebone contract named for, and there is a function called run. We can make it return a value. Okay, we can run the logic inside this function by using forge script, and the path for this script, you can see this function is run as a script. What forge script does is looking for a run function inside this path. If there are multiple contracts inside one source file, you can specify the contract after the path. Okay. And after running the script, it will show you the result, and it will show you the gas used. You can use this script functionality as a playground. For example, let me give you an example. Here we inherit from the script contract from for the same library, so that we can have the console, the log ability. So if you want to know the difference between API.encode and the API.encode path, you can write this as a script inside this run function, and run it by using forge script. Okay, we should use log bytes because we are logging out bytes type. Okay, here we can see the here we can see what's inside bytes A is the API standard encoding for this byte, and what inside the variable bytes B is a packed version of the string ABC. And what's more important about script is that it can it can send some transaction to the blockchain. The script provides a functionality, provide a cheat code called broadcast, or you can use .broadcast. Stop broadcast. And here we import our wrapped user contract, and we can deploy our wrapped user contract here. Here it tells us if we want to simulate on-chain transaction, we can pass the RPC URL. Okay, so here I pass my RPC URL for the quality testnet. Increase the verbosity level. Okay, after using forge script and add a RPC URL and set the verbosity level to 4, we can see on the upside is the simulation locally, and on the bottom side you can see here is the simulation on chain. It's what would happen if we send these transactions between the inside this broadcast cheat code. Is what would happen had this transaction been sent to the blockchain. You can see here we can deploy a wrapped user contract at this address. So simulation on chain is not enough. It can give us some information or deploying a script, and it can also tell us the gas usage. What we want is to actually send this transaction to the blockchain so that our wrapped user contract is deployed to the blockchain. We can achieve this by append the broadcast dash broadcast to this forge script, and we also want to verify our contract. To verify our contract, we also need to send our EtherScan API key. We also need to provide our private key of the sender. And also the address of the sender. Okay. It runs the local simulation first and the on-chain simulation, and it record the on-chain simulation and then send the transaction. send the transaction to the blockchain. Okay. You can see on-chain execution complete success, and total gas fee, and the contract is deployed to this address. And the contract verification goes on. Let's go to the goal is a scan and see this address. It's created, and we can see the contract. Right, this is our this contract. It means this contract is verified in Gradle is a scan. And we can interact it by using ETHKL1. Okay, let us try to deposit. How about 0.1 Ether? We can use 0.1 Ether could be yeah, I think that's 0.1 Ether. Let's try that. Oh, okay. It's not way, it's Ether. So we can type 0.1. And we can check our balance here. Let's wait for this deposit to finish. Okay. Yeah, the balance should be 0.1 Ether. And we also want to withdraw it. So here is wait. This is the gas fee. Okay. Then we check our balance again. It's 0. Okay, as we expected. And yeah, I forgot to mention this. We can use first test gas report to have a gas estimation for our deposit and withdraw function, right? Okay. That's so much for the workshop. to conclude, you can write your smart contract in Solidity. You can also write your test case in Solidity, and also the your script in Solidity. So you will remain in Solidity land for during development, and there's no context switching. It's a better develop experience. Okay, and that's so much. That's all for my workshop.
Okay.
And if you want to learn more about smart contract developing and the app development, you can go to our DappLearning GitHub repo to learn more about it. Okay, thank you all for listening. Terima kasih.
Thanks, Alan. So we have a few questions in the chat, and first question is from Chichuan, and he asked how hard it is for a hard hat user to relearn Foundry. Like, what are the possible difficulties you may find when you learn Foundry?
It will be quite easy for hard hat user to transform to Foundry. You only because all your test case and script will be in Solidity. So if you can write Solidity, you can use Foundry to do smart contract development.
Cool. I also found something that is new, which is VM, and Xingxuan asked what VM stands for in Foundry.
VM is an instance for the cheat code. So there are a bunch of cheat codes. You can check the Foundry book at book.getfoundry.sh, and yeah, it has a bunch of this cheat code inside this cheat code interface. So VM is an instance of this cheat code interface.
Yep. Okay. Another question from Tu. He asked, what would commonly cause the test to fail?
Revert the assertion if the exact value doesn't match the actual value, the test will fail. So basically, if the test case it reverts, it will fail.
Okay. Yeah, and to ask again, would my smart contract be considered bug-free if all tests passes, or is there house cleaning we must do before running in production?
Pardon? Can you repeat the question?
He asked, would the smart contract consider bug-free if all the tests passes?
No, absolutely no. Actually, unit test is not enough. After we write some unit tests, the purpose of unit test is to help us gain some understanding of how our external API is called by the user. And only unit test is not enough for the security of our smart contract. Normally, after we develop our smart contract, we will do fuzzy testing. We'll write test code for fuzzy testing, for property-based testing. So what is property-based testing? Is that you need to come up with some invariant, some property that should hold within within the range of input. And then Foundry provides a function called fuzzy test. It will randomly input some value and see if this input will break this property. So you write your property-based test and you test it against a range of inputs and try to find some input, some edge case that will break your smart contract. Normally, we will not configure our smart contract bug-free. Yeah.
Yeah, to add on a little bit on that, even though the smart contract may pass the auditing, but there's no bug-free, like in the smart contract, there's still some risk to some hacker to hack into your smart contract. So yeah. And I think the final questions is from Hafiz, and he asks how we connect IoT devices with Ethereum smart contract.
I'm not an expert in this area, but I think it's by making some RPC call to the Ethereum blockchain.
Okay, and he also asked how we can simulate multiple entries for performance tests.
Let me think about it. Performance test. Because many variable will affect whether your transaction will be accepted in the blockchain block. The latency and sometimes the relationship between your RPC node and the mining node will influence the performance. Yeah.
All right. So I think that's it. Anyone still have any questions? Okay, and if no, I think that's a wrap. You guys can find the recording in our YouTube channel. It's called Ethereum Malaysia. So yeah, lastly, thank you, Alan, for having this amazing workshop, and thanks everyone for joining us this evening. And yeah, thank you. Have a great evening.
Thank you all for listening.
Bye.
Yeah, good night.
Bye bye.